is on 5.1 functions. So the definition will begin with what a relation is. And a relation is a collection of ordered pairs. So, collection or a set, as we say. Here we have an example of a relation that consists of the set of the four ordered pairs 0, 3, 0, 4, 1, 5, and 2, 6. So note that it's possible to have the same first entry in two or more ordered pairs in a relation and then have different second entries. All right. And then we have a definition, the domain of a relation. Well, the domain of a relation is the set of all first elements of the ordered pairs. So in R here, that we have ordered pairs 0, 3, 0, 4, 1, 5, 2, 6. And the first elements in those ordered pairs are the numbers 0, 1, and 2. 0 repeated twice. Well, when we list out those elements in a set, we only list 0 once. So 0, 1, and 2 are all the first elements of the ordered pairs in our relation R. And we have another concept, that of range. So range, the range of a relation is the set of all the second elements here of the ordered pairs. So we'll highlight in yellow sort of the key part of the definition. So notice the second elements, 3, 4, 5, and 6. And, well, the range here is 3, 4, 5, and 6. Okay. So we have an example here. State the domain and range of the relation T equals the ordered pair 5, 3, 6, 3, and 7, 4. All right. Well, notice that we have the first elements, 5, 6, and 7 here. Yeah. And the domain of T is the name of that set. And likewise, we have 3 repeated and 4. So here's the 3 and the 4. Now we have a you try it over here. So let's try it together. State the domain and range of the relation S equals the set consisting of -1, 7, and 2, 5, and 2, 3. Okay. Well, our first elements are -1, 2, and 2. So you can say DOM or short for domain. Domain of S is equal to the set -1, 2, and 2. So just -1, comma 2. And the range, or just RAN, of the set S is the set consisting of 7, 5, and 3. So we have 7, and it's customary to write them in numerical ascending order, so 3, 5, and 7. Alright. Next example, state the domain and range of the relation shown in figure 5.1. So we can take a relation and plot it on an XY Cartesian coordinate system, XY plane. So what do we have here? We have the set S equals 3, 2, -2, 3, -4, -3, 1, -3. And it looks like 3, 2 here, these tick marks seem to indicate unit scaling 1, 2, 3. Oh, well, we have the fight here, so they do. So over here we go out 3 and then up 2, and we get A. So this is A right here. And -2 here, 3, it says B. There's B. -4, -3, -4, -3. Okay, C. 1, -3. 1, -3. There we go. D. And then, of course, we get the domain. Here, 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 and then the range from the second elements of the ordered pairs in the relation, which we see here, here, and here. -3 was repeated, so it only shows up once, which is why the domain and the range are different sizes. And by size, I mean number of elements in the sets. Right, did we have a, you tried another, excellent. So we have a you try it here. State the domain and range of the relation shown below. So let's start with point A. Point A, we have unit scaling, looking at the 5s on the axes. A is -2, -1. So we have A equals -2, -1. And B looks like 1, -4. So B equals 1, -4. And C looks like 2, 1, 2, 3, 2, 3. So comma 3, and D, negative 2 to D equals negative 2, 2. Alright. So now we can state the domain and the domain, let's see, consists of, what do we have here? Negative 2. Oh, didn't want to do that. Negative 2, 1, 2, and negative 2. So repeated here. And we get negative 2, 1, and 2 for the domain. And then the range consists of negative 1, negative 4, 3, 2. No repeated numbers. So the minimum number is negative 4. Let me go back to black. Negative 4, 3. Oh no, negative 1, right? And then 2, and then 3. There's our range. As we can verify, negative 2, 1, 2, negative 4, negative 1, 2, 3. Alright, mapping diagrams. So a so-called mapping diagram is a useful construction that helps one to analyze a relation. Consider the earlier relation 0, 3, 0, 4, 1, 5, 2, 6, which had domain 0, 1, 2 and range 3, 4, 5, 6. To construct a mapping diagram for this relation, you want to list the elements from your domain vertically here on the left. And then from your range, vertically here on the right. And then you draw arrows from the elements in the domain to their corresponding elements in the range. So we have some instructions or some descriptions of how these arrows were drawn here, and we will proceed by an example. Looking here at example 3, in fact, create a mapping diagram for the relation in example 1. Let's see, what did we have in example 1? That was the set consisting of 5, 3, 6, 3, and 7, 4. So the domain here, 5, 6, 7 gets mapped to the range of 3, 4. So here we have 5, 3. Make that a little bigger. So 5 maps to 3, like so. And, and 6 maps to 3. So we have an arrow from 6 also going to 3. And then 7, 4. So 7 maps uniquely to 4. And just as we have here in the text below. So we have a, let's see, did we lose a you try it? Maybe so. Here. Now we will talk about functions. So a function is actually a special type of relation. So it turns out a relation is a function if and only if each object in the domain is paired with exactly one object in the range. So yeah, highlight this here. Exactly one. Alright. So for instance, 0 here is paired with 3 and with 4. So this is not a function because we have something in the domain paired up with more than one thing. However, t was also not a function. Or, excuse me, no, we have distinct, all the elements in our domain are distinct, 5, 6, and 7. So as long as the elements in the domain are distinct and everything's ordered pairs, then this is a function. So 5 corresponds to 3, 6 corresponds to 3, 7 corresponds to 4. If we were to take R say we're to take R and we have 0 in the domain, 1 in the domain, 2 in the domain, and then in the range of the relation R, we have 3, 4, 5, 6. note that 0 maps to 3 and 4. 1 maps to 5. 2 maps to 6. So here, this is not a function. Because the element 0 maps to more than one thing. In the range. Whereas T, consider T. So in T, we have, what was it, 5, 3? And 6 in the domain maps to also 3. And 7 in the domain maps to 4. So 5 maps to 3, 6 maps to 3, 7 maps to 4. So T is a function. Because it's okay for 2 things in the domain to go to 1 thing in the range. It's not okay for 1 thing in the domain to go to 2 things in the range and still be a function. So T is a function. Because each element in the domain maps or corresponds to 1 element in the range. Clean that up. Right. It's a little tricky, but once you got it down, it's not too bad. So let's see here. Is this relation? It's a relation. It's 5 ordered pairs. So is this relation a function? Well, I can tell you right now, no. And graphically, when you see a vertical line, if you can draw a vertical line through 2 points of a relation, then it can't be a function. And then, well, let's just take these. We see the scaling here, 5 and 5 respectively. So the points are 3, 2, and 3, 3. So if we have 3, 2, and 3, 3, then we have 3 in the domain, and in the range we have 2 and 3, and 3 is mapping to 2 things. So not a relation. How about our you try it over here? Well, notice that vertical line through A goes through 1 point. Vertical line through B, 1 point. Vertical line through C, 1 point. Vertical line through D, 1 point. Vertical line through E, 1 point. The mapping diagram would be -3, angle 1, -3 maps to 1 and -2, or excuse me, -1, -2. Here we have 0, 3. Here we have 3, -1. Here we have 4, 2. Yeah. This point uniquely maps to this, well, this element uniquely maps to this element. This element uniquely maps to this one. Likewise here, here, and here. So this relation is a function. All right. So we have some further examples here. Example 5. The following relation pairs automobiles with their gas mileage. Determine if the relation is a function. Well, you have the Bentley Mulsanne, which gets 18 miles per gallon, a Kia 30, a Lamborghini 20, Smart 21, and the Jaguar 23. Alright. We have how many? 5 different cars. And so none of the car brands were repeated in this set. For instance, we don't have the Kia mentioned twice. Kia's mentioned once. Bentley's once, Lamborghini once, Smart once, Jaguar once. And when we display out the mapping relation down here, we can see the unique relationship between the elements in the domain and their counterparts here in the range. We don't have anything in the domain mapping to more than one element in the range. We have everything in the domain mapping to exactly one element in the range. So here, let's see, perhaps they tried to throw us a curve with Mary and Maria, or Joe and Zoe. Similar spellings, but we have distinct names. And each of those names is paired up with a number. So, function. Right. Following relation pairs a particular bird with the state that has adopted that bird as its state bird. Determine if the relation is a function. We have the yellowhammer for Alabama, the robin in Connecticut, the nean in Hawaii, and the robin in Michigan. Well, note that robin is the first element in 2 ordered pairs. And we have different second elements. So robin, put in quotes, maps, or is sent to, or is paired with. We'll say paired with, like our text. Robin is paired with 2 different states. So, this relation is not a function. We have another you try it here. Let's see, the following relation pairs people with cars that they own. And we scan through, what do we want to do first, right? We want to scan through the elements of the domain, so the elements in the first slots of the ordered pairs. And we see Bernard twice, and Kate twice. So Bernard is paired with station wagon and sedan. That right away is enough to say not a function. So we have old Bernard here, and he maps to station wagon, sedan. And we have Kate. Freeze. There we go. Kate maps to sport utility. And she's paired with minivan. So, no. Because two elements in the domain have multiple elements they are paired with. So, no. Mapping diagram notation. Right. So here we want to introduce function notation, which we use letters for, Latin letters. So this mapping diagram here tells us the function f. So that's the name of the function. Maps or pairs the number 1 with the number 2. And then f is what is a map? It's a set of instructions for figuring out terrain. That's what we usually mean when we talk about maps. So think of functions are rules. They're sets of rules. F maps 2 to 4. It maps 3 to 6. It maps 4 to 8. So we use these arrows here to indicate the mapping or the assignment of 3 to 6. Right. Another word we use is send. F sends 4 to 8, for instance. So now notice back here that 1 is sent to 2, and it's no coincidence that 1 times 2 is equal to 2. 2 is mapped to 4. 2 is paired with 4, or 2 is sent to 4. What do you do to 2 to get 4? Well, one thing you can do is take 2 and multiply it to itself. And that will get you 4. Alright. Well, what about 3? How do you send 3 to 6? Well, you can take 3 and multiply it by 2, and that will get you 6. How do you send 4 to 8? Well, you take 4 and multiply it by 2, and that gets you 8. So notice that the pattern seems to be that you will get your given some number in the domain, you get the element it is paired with in the range by multiplying it by 2. And which suggests this notation. So what do you do to some number for this function f to get another number? Well, you multiply it by 2. So to send x to its corresponding element in the domain of f, you multiply 2 to whatever x is. Let's try one for ourselves using this function. What would f map 20 to? Well, 2 times 20 is 40. Oops. What would f map 32 to? Well, it maps it to 2 times whatever you put into the function. And 2 times 32 is 64. Alright. So here's a rule. F takes x, it multiplies 2 to x, and then adds 3 to that product. So where does f send 8? Well, f sends 8 to the number that you get from multiplying 2 to 8 and then adding 3. 2 times 8 is 16. 16 plus 3, yeah, that's 19. So suppose we have f and it sends x to 3x minus 5. So where would it send negative 2? Well, we would have f negative 2 and send that to 3 times negative 2 minus 5, which is negative 6 minus 5, which is negative 11. So the answer is the function takes negative 2 and maps it, or pairs it, or sends it to negative 11. Alright, how about x is sent to the function x divided by the quantity x plus 3. Where does f send negative 1? Let's try it out. So f will take negative 1 -1 divided, I would prefer to use a horizontal, division symbol. So it will take -1 and divide it by -1 here. Plus 3. And that is equal to -1 over -1 plus 3 is +2. So f takes -1 and sends it to -1/2. Alright, so suppose we have this rule. X maps to 2x squared plus 5x. Where does f send 3? So f takes 3 and pairs it with the number that you get from taking 3. Take 3, square it, then multiply 2 to the result, and then add the number you get from 5 times 3. So see the connection. Whatever number's here goes here and here. Like we have here 3 here, so 3 goes here and here. And then that is 2 times 9 plus 15. 18 plus 15, which is 33. So f takes 3 and maps it to 33. So let's try here. If f of x is 3x squared minus 20, find f of -3. Well, f of x is 3x squared minus 20. So f of empty parentheses equals 3 times empty parentheses squared minus 20. And since we're evaluating -3, we plug -3 in here, and likewise in here. -3 squared is +9, so 3 times 9 minus 20. Well, that's 27 minus 20. So 7. Thus, the function evaluated at -3 is equal to 7. And we have g of 2. Well, g is 4x plus 6 divided by x. And it's g of 2. So g open parenthesis equals 4, where if there's an x open parenthesis, right? So 4 open parenthesis plus 6 divided by open parenthesis. So g of 2 means plug in 2 wherever there are open parentheses, and then evaluate. So we work vertically. Here we get 4 times 2, so 8. Next term, 6 divided by 2, well, 3. So 11. Thus, g of 2 is equal to 11. It says g of 2 is equal to 10. Did I make a mistake? 4 times 2 is 8. 6 divided by 2 is 3. 8 plus 3, definitely 11. So it looks like we have some errata right here. It's 11. Interchanging y and f of x. This can be a little tricky. So in most cases, y and f of x are completely interchangeable. I have to look at the context. Here we have y equals 3x plus 7. Find y when x equals 5. Well, if x equals 5, we can replace x with 5, which we do here. And we have y equals 15 plus 7. Well, y is equal to 22. Okay. And in our function notation, given that a function f is equal to 3x plus 7, evaluate f of 5. So it's saying put 5 in the place of x. If you do that for the function f, you'll get 3 times 5 plus 7. So when they replaced the x with 5 in the function, the x becomes 5 here. This numerical expression simplifies to 22. So in each case, the answer is 22. In the first case, we have y equals 22. And it's not, directly evident that the x value of 5 was used to get this 22. However, on the other hand, for function notation, we have f of 5 equals 22. So we have a result, and we're told what number was used with what function to get that result. So that's an advantage of function notation. So here is a demonstration of why y and f of x are interchangeable. Sketch the graph of f of x equals 2x minus 3. Well, they did that, and it's no different than building an XY chart. So say you put in 0, then you get y is equal to 2 times 0 minus 3, which is minus 3. You put in 1, you get y equals 2 times 1 minus 3, negative 1. If you were to use function notation, you have f of 0 equals -3 f of 1 equals -1, etc. So sketch the graph of f of x equals -2/3 x minus 2. Well, that's the same as graphing the linear equation y equals -2/3 x minus 2. We see a slope of -2/3 and a y-intercept -2. So y-intercept -2, and then we drop 2, so right 3. So now let's do some exercise. Here for 2, so here we have domain is the set of what? 6, 3, 2, and 8. So 2, 3, 6, 8. And here, this is the range. 4, 3, 5, 7. So 3, 4, 5, 7. And 5. We have a domain of 4, 4, 5, and 0. So 0, 4, 5. And a range of 7, 8, 0, 7. So 0, 7, 8. And we can say that S is a function because all of the elements in the domain are distinct. T, however, we have 4 here twice, and it has different values, 7 and 8. So, not a function. So, for 8, we have domain. Let's look at the coordinates of these points. It looks like -1. Coordinates here, 1. X coordinate here, or not. 3 here, 4 here. So domain -1, 3, 4. Let me make that look more like a brace. And the range looks like -2 here, 4 here, 1 here, -4 here. So in the range we have -2, well, -4, -2, 1, and 4. And determine whether the given relation is a function. So 12. We see -8, -4, and 2. So distinct. Whereas, notice here for 15, we have 1 and 1. So 1 in the domain is mapping to 6 and 8. T is not a function. Alright. Determine whether the given relation is a function. Well, notice here we have a vertical line through these points. And those points are 1, 1, and 1, 2. So, same element in the domain mapping to 2 different elements in the range. Whereas, say here, we have vertical line, vertical line, vertical line, all going through one point. So this is a function. So that's f of x equals 3x squared plus x plus 6. F of -3. 3 is 3 times negative 3 squared plus negative 3 plus 6. So you plug in, and then 3 times 9 minus 3 plus 6, 27, minus 3 plus 6, and then negative 3 plus 6 is 3. So 30. And so we have f of negative 3 is equal to 30. About 33. F of x is square root of x minus 7. Evaluate f of 88. So f of x equals square root x minus 7. Evaluate at f of 88. Well, we have f of blank equals square root of blank minus 7. So step 1. Replace variable with open parenthesis. And then plug in the value. Plug in the number being evaluated. So that's 88. That goes here. And 88 minus 7 is 81. And the square root of 81 is 9. So f of 88 is equal to 9. And, and that concludes the lecture 1.